Here the barrel weighs 100 pounds. They don't give us any information about the density of the barrel or where the center of the barrel should be. In my assumption, just to be able to even do this problem, I'm going to assume the barrel is uniform. And now let me put the weight of the barrel in its geometric center. If I had more information that was filled with water halfway up or something like that, then that might change. But without that information, I'll just say it's uniform and analyze it that way. We're told that between the barrel and the floor, the coefficient of friction is 0.5. We want the minimum value of P to cause motion. Sometimes there's only one way it can move. In this case, there's going to be multiple ways that motion could occur, and we have to separate out those different methods. So before we get to the free body diagram, what possible motions could occur when we apply this force P to the barrel? Right. We could see it sliding to the right, probably, on the floor when we're pushing it. And what else could happen when we push on the barrel? Right, it could tip over. We would presume at the bottom right corner. We're ignoring the fact that by pushing it, the man could slip. That could be another form of motion. So it's only going to be down to two forms of motion for this one, slipping on the floor or tipping at the bottom right corner.
If we were given information about the man, that would be a second free body diagram.
Right, that would be kind of similar to the quiz. If we knew like the coefficient between his shoes, his weight, and his center of mass, then it would be another free body diagram, and then also when we're considering the different methods of motion, we're going to say, does he slip first? Does the barrel slip first? Does the barrel tip first? Potentially, does he tip first? So in this case, only two forms of motion. They'll be more simplified than some of the other examples we looked at. So we start with the free body diagram. We only need that of the barrel, since that's the only thing that's going to be moving in this case. We're given the dimensions. It's 3 feet by 4 feet. I'm making the assumption that the barrel is uniform, so the center of mass is at the center of the barrel. And we're applying this force P at the very convenient 3-4-5 ratio triangle. So that's the applied load, that's the weight. What other forces act on the barrel? Normal force, this is a surface in contact with a surface. So in this case, we do have some normal force. And this is where if we do have to consider tipping, and in this case we do, I'm going to say that that normal force is a distance d from the point we presume it's going to tip about. There were cases where we didn't have to include that distance. If we didn't know the length of the barrel, or if we didn't know any of the length dimensions of the barrel, we wouldn't be able to do a moment equation, and we could ignore it. Or if it's a point in contact with a surface, there's only one place the normal force can be. So two surfaces in contact, that's where this comes up. And then what other force is going to be acting on the barrel? Friction force. We would think that if we push the barrel to the right, it would be traveling to the right, which means that the friction force would oppose that motion and point to the left, parallel to the surfaces they're in contact. So we have an unknown normal force, an unknown distance away from a pivot point, we have an unknown friction force, and we don't know how hard we're pushing the barrel. So this is our complete free body diagram once I have the coordinate system here. Our complete free body diagram for this situation. From the free body diagram, well, we get to the equations next. First, the ones that are going to be true, whether we're considering tipping or slipping, the equilibrium equations. As long as it's in static equilibrium, which in every circumstance it will be since we're looking on the verge of motion, these are going to be true in any scenario. If we sum forces in the x direction, we'll have a component of force P, and we'll have the friction force to the left. In the y direction, we'll have our unknown normal force. We'll have the weight of the barrel and the vertical component of our applied force P. I'll reiterate again, do not assume that the normal force is equal to the weight. It may be true, but let the equilibrium equations tell you that. Do not assume that up front. In this case, we'll see that the normal force is going to be greater than the weight because we're pushing into the ground while we're pushing that barrel. So normal force is not going to be 100 pounds unless we weren't pushing at all. But in general, it's not equal to the 100-pound weight of the barrel. And if we sum moments, usually the best plan is to sum moments around the potential pivot point, but the moments around any point will be 0. If we sum moments around this pivot point, the force of friction will not be included. I'll have the moment due to the weight, so 100 pounds times 1.5 feet. I'll have the horizontal component of my applied force, so the 4/5 p, horizontally, so it has a perpendicular distance of 4. And it's going to be clockwise around Q, so it's negative. I have the vertical component of the applied force P, 3/5 p. That will have a perpendicular distance of 3 feet from Q. And finally, I'm going to have the normal force times the unknown distance away from point Q, which I called small d. These are my equilibrium equations. I haven't yet said anything about on the verge of slipping, on the verge of tipping. These are true when I'm in static equilibrium. I have 4 unknowns, and I have these 3 equations right now. Like we saw in some of the other tipping, slipping type of problems, it sometimes is nice to now rearrange this, since P is what we ultimately need to find. If we find all of our other 3 unknowns in terms of P, it's going to make the solution a little bit easier, although you don't have to do that at this step. But I took my equation 1, I solved for the force of friction in terms of the applied force, is 4/5 times P. I can find my normal force in terms of that applied force. And I can find the distance of where the normal force is located, or the equivalent normal force is located, by solving this. For n, I put in this definition here, so I get that d is going to be 750 minus 7p over 500 plus 3p. Or you can leave these as is and then do the substitutions as you go. So still, I just rearranged these, still 4 unknowns for 3 equations. This will make the next step easier to find the value for P, though. We're out of equilibrium equations. Now we have to start partitioning it by the different scenarios. So we talked about the 2 possible motion scenarios. The barrel slips relative to the floor, or the barrel tips at Q. So now for our additional equation or equations, we have to have the different scenarios. So I'll call the first scenario A. The order doesn't matter, but just to match my notes, I'll say scenario A is the barrel slips. What equation or equations become true when the barrel is on the verge, I should say, is on the verge of slipping? Right, the friction force is maximized when we're on the verge of slipping. So for A, I'm going to maximize my friction force. So Fr is going to be mu times n. I know my mu is 0.5. So the force of friction is equal to 0.5 n in scenario A. Now, between equations 1, 2, 3, and 4a, I have 4 equations for my 4 unknowns. So if I put equation 4a into these 2 equations here, I can find the value of P. So solving 4a, if I call this 1.1 and 2.1, I get that the force, the applied force would have to be 100 pounds for this to be just on the verge of slipping. Right, so that scenario is done. So now I have to consider the alternate possibilities. In this case, just the one alternate is that it tips at Q. or again, is on the verge of tipping at Q. Equations 1.1 to 3.1 are still true, but now I have a new equation 4, and again, potentially more here. So what new equation or equations will be true in scenario B when it's on the verge of tipping? Right, D equals 0, which is to say that on the verge of tipping, the equivalent normal force is going to be directly beneath the pivot point at Q, which means that this value of D is 0, placing N directly beneath Q. So for scenario B, I now take equations 1 through 3, or 1.1 through 3.1, and 4B, and solve those 4 simultaneously. Again, I'll point out, we've used this equation. It's only true in scenario A. We have a different equation 4 in scenario B. I take equation 4B. If I put that into equation 3.1 and solve, I get that the force it would take for it to just be on the verge of tipping at Q is 107 pounds. Those are the only 2 motion scenarios that we came up with here. So finally, what we have to do, we have to kind of, from our results, make a determination of what's going to happen, of what it takes to cause motion and what happens. So we have 107 pounds for it to tip, 100 pounds for it to slip. We're looking at what's the minimum force required for motion, therefore the 100 pounds. So the minimum required is 100 pounds. The barrel slips.